All right. So, and motion instructions are instructions that tell the robot arm how to move. Okay. And of course, there's lots of different manufacturers of robots, and so the exact layout of the motion instruction may vary between them. So we're specifically going to be talking about the FANUC robots uh, today, and I'll show you some demonstrations using the Roboguide software that I introduced to you last week. Okay. So when you look at the motion instruction, there's basically 5 parts to this motion instruction. Okay. So the first part here is what they call the motion type. Okay. And so there's 3 main motion types for the FANUC robots. The first type is joint, the second is linear, and the third is circular. Okay. Then the next part is what they call the position type. And so there's 2 types or 2 ways that you can store the position. All right. And so what the motion instruction is the instruction telling it to move to this position. Okay. And how to move there. Okay. So we can store that position in 2 different locations or 2 different types of locations. The next is the speed. How fast do we want the robot to move? The fourth is the termination type, telling it, what to do when it gets to the point, if it gets to the point. And then the last one, or the 5th one, is an option. Okay. All right, so let's go ahead here and look at the motion type. Okay, and so I kind of already mentioned there's 3 primary motion types. So there's a joint, there's linear, and there's circular. Okay, and if depending on, maybe you might have some additional software package or maybe newer versions, then obviously there could be some other choices. But these are the 3 basic motion types. Now notice this number 3 says circular. It doesn't say circle. All right. So what it does is it basically moves around a half circle. Okay. But let me just go on down here then, and we're going to kind of see. I'm going to show you the differences of these in a little bit. I'll demonstrate that. All right. But here's just kind of a pictorial picture of that. So what the joint movement is it's moving. It's kind of a natural movement. All right. So it's, if you think about like your arm, your body, if you want to move your hand, your fingertips, let's say this is my finger here, and I want to move it from point 1 over to point 2. Okay, I could go in a straight line, which of course we all know that a straight line is the shortest distance. However, it's not a natural movement. To try to move your hand in such that the tip of your finger is moving in a perfectly straight line, honestly, with the human body, it's pretty much impossible to do that unless you have some kind of roller or yardstick or something that you're following along. It's pretty hard to move in a perfectly straight line because our arms don't really move that way. They move more in a natural sort of arcing sort of motions. And that's exactly the same for robots. These robots have rotational joints on them, and so they're not really designed to move in a straight line. Okay, unless we're talking about, if we go back and we talked about the Cartesian type of robots way back in week 2 or whatever, when we were discussing those like to move in a straight line, as long as the straight line is in a perfect X or a perfect Y or a perfect Z sort of orientation. All right, but if it's at some sort of angle, we just don't move that way. So and that, like I say, that's true for most robots. We're just moving from one arbitrary point to another arbitrary point. It's actually easier and smoother for the robot to make that move by just sort of doing some kind of arcing sort of thing. Okay, the problem with the joint movements is that we don't fully understand how the robot is going to get there. We're telling it to go to point 2. That's the destination. All right, so notice here's the motion instruction. So it's a joint movement telling it to type, and then it says go to point 2. Well, here's point 2, but what it doesn't tell you is whether you're going to go to point 2 from point 1 or from some other point. Okay, so if the robot happens to be up here, where my little pointer, red pointer here is, and this thing starts moving, okay, if I tell it to run this instruction, but the robot is up here, it's going to move over to point 2 from this direction, all right, not from point 1. So in this picture, it's implied that the robot is starting at point 1. But if you, for some reason, stop the robot and jog the robot somewhere else, and then you run this instruction, it's going to move from where it's at over to that instruction. It's not going to move to point 1 first unless you have an instruction above this one that says go to point 1 first. Okay, so that's also very important to remember when you're working with these robots, is if you stop a program somewhere and then move the robot for whatever reason and then restart the program, it's going to start moving to point 2 from wherever it's currently at, not from wherever the program said to go at before, because you've interrupted it and you moved it, and so it's in a different location. All right, but a joint movement is more of a natural movement. Okay. But as a slide just said, it's not predictable. Now, on the other hand, a linear movement is very predictable. With a linear movement, we know we're going to move in a perfectly straight line, okay, from point whatever to some other point. Okay, now again, if we interrupt and the program and then jog the robot over here, now it's going to do a linear movement from here over, not from point 1 over. Okay, but it's going to move in a perfectly straight line, so we know it's going to move in a straight line. Okay, the other thing that really impresses me about these robots is, this here up here is the speed of the robots. This is how fast it's going to make that movement. And the thing that really impresses me is the fact that it can move from this point to this point at a steady speed of 100 millimeters per second or 1,000 millimeters per second or whatever that you set it to, up to the maximum, obviously. But it's going to make that move without, it's going to make that move, and it's going to move all 6 axes simultaneously to get from point 1 to point 2. But not only does it do that in a perfectly straight line, it does it at a constant speed. So the whole time it's traveling from this point to that point, it's going to move in a perfectly straight line and at a very constant speed. It's going to move at this speed. Now, that's not 100% true, because it's got to get up to speed. So if it was sitting here at position 1, not moving, it was at a dead stop, then it has to accelerate. So it's got to actually speed up. But then once it speeds up, once it accelerates and it gets moving up to this speed, it's going to stay at that speed until it gets near point 2. Now, if it's going to stop at point 2, then it's going to have to slow down. So what it'll do is it'll actually start slowing down before it gets to point 2. So there's a little bit of acceleration time and deceleration time. However, it's going to, once it gets up to this set speed, it'll maintain that along a straight line until it gets to the point where it knows it should probably start slowing down if it's going to actually physically stop at point 2. All right, so but that's the linear movement. All right, now the circular movement is more of an arcing sort of movement. Okay, and so notice here with the circular movement, this is one of the things is that you got to get, and I sort of was talking about this before, you got to get to the beginning of an arc. Okay, so think about it. If you're going to like take a piece of paper and you want to draw on a piece of paper here. All right, well, here's my pen and here's the piece of paper, and I'm drawing a circle, but the circle's not going on the paper because it's not touching the paper. So you first have to, if you're going to draw a circle, you first have to get to the circle, then you can start drawing. I don't know if you can quite see that there, but so if I'm just here, I'm not drawing on the paper. I have to get to it. So before you start a circular movement, you have to be at the starting point of your circle. And then the circular movement now is going to have 2 points. It's going to have kind of the halfway point and the final point. All right. And so it's going to map out an arc here, but you've got to get to that point. So you notice here in this example, the first point in this case is a joint movement. The joint movement is getting me to the start of the arc. All right. So the circular movement doesn't include point 1. The circular movement only includes point 2 and point 3. All right, so those are the 3 motion types. All right, so you can read through these slides obviously, and I've got a lot of details, so I'm talking about them, so I'm not going to sit here and read and look at every single slide. All right, so here now we're talking about where are we going to move to, right? So we have the way we're going to move, the motion type, and then the position we're going to move to. Now, again, that position is assumed that we're in a program, so we're starting off here at some point wherever up here. But if we're not at that point, then then it's going to start from wherever it's at and move in that method. So, but we have 2 types of ways of storing the information. The first type is in what we just call a point. Okay, or sometimes position point. All right, and then the other one is called a position register. Okay, points are stored in the program itself. So like right here, it's talking about point 1. Well, point 1, whatever point 1 is 1 point in space. Okay, it's 1 point in space, and point 1 in this program is unique to this program. So if you create a new program and you store a point 1 in that program, it's a completely different point. Position registers, on the other hand, are kind of a global value. And so when you save a position register, you're saving that point in space, and that position register now can be used by any program. All right, so if you have 1, 2, 3, 4 different programs and they're all using this position register, okay, then, and they also have to be using the same frames. And we haven't talked a lot about frames, but the position register stores the frame. And so, and the points also store the frames. There's 2 primary types of frames. There's the user frame and the tool frame. And we talked a little bit last week about like the tool frames and setting them up using the Roboguide software. But when you then create these points, it stores that point in space based on your current frame of reference. Right? And so as long as you're both using the same frames, this position register is the same point in space no matter which program is referencing it. But a point is unique. All right, so the third is the speed, okay? So this third value here is the speed. And the speed, again, tells it how fast it can move, all right? But the choices for speeds vary depending on the type of motion. So if you're doing a joint motion type, so if it's a J type, a joint motion type, you only have 3 choices for your speed. The first choice is a percent of maximum speed that the robot can move. All right, so it could be 100%, it could be 50%, it could be 5%. Okay, so it's got to be an integer value. You can't be like 2.5%, but it's a percent of the total max speed of the robot. The other 2 settings here are either seconds or milliseconds. And this is kind of cool because, again, what you're doing is you're saying, I want you to go from point A over here to point B, and I want you to take 3.2 seconds to get there. All right. And the controller will calculate which joints it's got to move at what speeds to move that tip from point 1 over to point 2 and get there in exactly 3.2 seconds. Okay. And so, or milliseconds, you know, say go get there in 50 milliseconds or whatever. Now, obviously, you know, there's a maximum speed to the robot that it can't exceed. So if the points are too far away, you know, and you're trying to travel this huge distance and you're saying go from here to here and do it in 1 millisecond, it may be impossible for it to do that. All right. But as long as your distance is within, you know, the speed rating of the robot, then you can tell it, you know, get there in this many milliseconds or this many seconds. Right? Now, linear, if you look over here on linear and circular, okay, they don't have a percent choice. Okay, they have, instead of the percent choice, they have millimeters per second. Okay, which means that it's going to either move in a perfectly straight line at so many millimeters per second, or if it's a circular, it's going to be moving around that arc at you know, so many millimeters per second. Or if you wanted to, you could use centimeters per minute. So remember, there's 10 centimeters in every millimeter. Okay, but they give it to you in minutes here. So you can say, well, I want you to move so many centimeters per minute. Okay. Or if you want to do the American way, right, we can do inches. So you can actually tell it to move so many inches in a minute. All right. Or you can tell it to move degrees, right? So if you're going around an arc, that's degrees. So you can tell it to move so many degrees per second. Now, if you look over here in linear, they also have degrees per second. And you may say, like, well, wait a minute, why do they have that? Well, remember that even though you're going to be moving in a straight line for your main axes, right, you can still like rotate the faceplate or whatever. And so you can do rotation, you know, you can rotate the tooltip or whatever. And so you could, you know, in that case, then degrees per second would be a logical choice if you wanted it to be rotating at, you know, 3 degrees a second or 12 degrees a second or something like that. Or you can do, like over in the joint, you can do seconds, and milliseconds are also choices there. Okay, but these are the types of speed choices that we can choose. All right, so now when we're talking about a point, and we talked some about this last week, remember that the green ball and the Roboguide software was the tool center point. And so when we're talking about a point in space, we're talking about this point, which is the tool center point. So whatever that tool center point is that we've defined based on our tool, then this point in space, this point right here in space, is this point. However, notice I got 3 different robot arms, or 3 different configurations of an arm at least, coming to this same point in space. So here's one point in space, but over here I'm coming at it from the right hand side, and over here I'm coming at it from the left hand side, and over here I'm coming in straight at it. So we can actually come at it from multiple different angles. All right, so I'm going to skip ahead to another picture here, come back to these other ones. But we have, when we talk about a point, okay, this is the information stored for a point or a position register. So you notice I mentioned that there's the frames. So there's the user frame and the tool frame. All right, so anytime you save a positional point, whether it's a point in the program or a position register, you're storing the frame reference. There's a tool frame reference and there's a user frame reference, and you're storing both of those as part of this point. Okay, and then you're storing the actual location, X, Y, Z, and you're also storing the yaw, pitch, and roll. Okay, so all this information is stored in a point. Okay, so you've got the frames, and again, what it's talking about is that tool tip. Wherever the tip of that tool is, that's what it's talking about. However, along with all that information, there's this extra piece called the configuration. Okay, and because when we look at this, right, we can come, we're talking that point that you're talking about is this point in space. But we can come at that point in space from lots and lots of different directions. Okay, I mean, virtually an infinite choice of directions. We can come in like it from here, or we can come straight down, or we can come over here, or we could come from the front. All right, so we could come at this point from virtually any selection of angles. Okay, and so that's part of the angle information is stored is this configuration piece. All right, so you see, like this says nub. Well, nub means you're not flipped. Okay, you're in an up position, but you're backwards. Okay, so if we look over here, this kind of shows you flip or no flip. So no flip is kind of with axis 5 coming down. Flipped would be like if you flip your hand and you're coming up from underneath. Okay. Up and down talks about joint 2 over here. So at joint 2, you're either coming, like your whole arm is coming down this way. All right, you could still be flipped over there, but your kind of shoulder blade is kind of either coming up this way or underneath like this. Okay, and so then so that is like the flip and the non-flip, and the backward is like if you're actually kind of think about if you're kind of bent over backwards. All right, so this picture here, you know, the robot is totally bent over backwards. Okay. So this anytime you store a point in XYZ format, then you're actually storing it user frame and tool frame, this point in space, but you're also, along with that point in space, you're storing your configuration. How did you get there? Okay, because you're coming to this point. Here's the tip of my pen. So I'm coming to this point, but did I come over from this angle? Did I come up from the front and underneath? Did I come from back behind, or did I kind of flip over and get to it like that? How did I get to that point in space? So it's one point in space, but it also has to tell it how it got there. And that's this configuration piece. And what you run into a lot when you're programming these robots is if you're trying to change the configuration, a lot of times you run into a configuration error. So you have to kind of walk it through when you're changing the configuration from flip to not flip, or up to down, or front to back. Anytime you're doing that, you are you know, anytime you're kind of changing that piece there, it's going to it's just going to give you a configuration error if you just, you know, if you just like say, well, go from this point to this point, and the only thing different is like the configuration, it's going to give you an error. So if you try to get to like this exact same point, 913 x minus 42y and z 379, if you were trying to get to this exact same point, but all you did was change your configuration from NUB back to NUT front, and said go to the same point, but you know, kind of flip over the other way, it won't do it. It'll give you a configuration error. So what that means is you kind of have to walk it through these configuration changes, making small changes until you get it where you want it. All right. Another error that you see a lot is what's called a singularity error. The singularity error is typically associated with J5, and that's when the pointer is the J4, 5, and 6 are all like pointing straight out. And then when you know, if you're trying to go to this point, it doesn't. The robot can't decide whether it should go this way or this way. But if it's pointing, if you got like J5 sort of at an angle, then it knows, hey, let's go down that way instead of go up. And so so the singularity will pop up. Now, when you store your information, okay, over here I was showing this is the XYZ yaw, pitch, and roll. And so when you store it this way, it's got user frame information, tool frame information, and the configuration information. All this information has to be stored. However, remember that technically this robot just has 6 axes, okay? And so instead of storing all these different pieces, you can simply store what is the current rotational angle that for J1, how many degrees is J1, how many degrees is J2, how many degrees is J3, 4, 5, and 6. And you can store it in degrees. And when I get onto the simulation software here in a minute, I'll show you that. All right, but before we get there, let's just talk about the termination piece. Okay, so the fourth element is the termination. And there's 2 choices under there. One is fine, and the other is continuous. So we have either fine or continuous. Now, continuous has a number associated with it between 0 and 100, which is basically a percentage. Okay. All right, so fine says that you're going to go to that point and stop at that point. Okay, so if you're using a fine, it says you're actually going to stop at that point. Continuous, on the other hand, says we're not going to stop. All right, And so if you do like a continuous 0, it's kind of like, I know none of you guys would ever have done this, but like if you rolled through a stop sign. All right, so you're kind of coming up and there's a stop sign and you slow down and then you look and there's nobody coming the other way. So instead of stopping, you just kind of, just kind of coast right on by. That's kind of what this continuous is. The continuous is you're just going to kind of very slowly, you're going to slow down, but you're not going to do a dead stop. You're just going to kind of roll on through that point. All right. But if you increase this to 100%, now what 100% says is I ain't slowing down. Okay. I'm just going to cruise on by and I'm going to get maybe kind of close or maybe not so close. And so when this ranges between 0 and 100, 0 is basically going to get to the point but not stop at the point. 10% says that we're going to slow way down and we're going to get really close, but we're not going to stop and we're not really going to hit that point. 100 says we're just going to cruise on past and we're not even going to stop. Okay. All right, so I've got like a little graphic here trying to show this. So with the fine termination, okay, so with the fine termination here, we're going from point 1 to point 2, and then our next point is point 3. And if we're using a fine termination on point 2, it says we're actually going to get here and we are going to stop. Now we may only stop, boom, just for a microsecond, but we're actually going to have a stop. Okay, may not be for very long, but it will be a complete stop. On the other hand, here's some examples trying to illustrate the continuous. So a continuous 0, we might not even quite get to the point, but we're going to be really, really close, and we're just going to move slowly past. Okay. Continuous 50 is out here. It's like, yeah, we're going to kind of slow down and wave as we go on by. Continuous 100. Well, continuous 100 says we're not even slowing down. We're just going to we're curving over this way because this was where we were supposed to go, but our final goal is over here. So we're just going to kind of make a smooth curve and we're going to kind of swing over that way, but we are not slowing down. All right, so the final is an option, okay? So option means that you don't have to have it. It doesn't have to be there. Some different options that we can do is, like if you've got a tool that's a spot welder, you can actually tag on here. We'll go to this point and then boom, make a spot weld and then move on. Okay, so you can actually do that in one instruction. So you move to the point, boom, do this spot weld, and then move on. Okay. You can actually, I was talking about how you have to accelerate and decelerate. There's some different choices here that you can add this option to change the default acceleration choices. Okay. So you can tell it to maybe accelerate a little bit faster than the default would, or accelerate slower. So if you're carrying a really heavy piece, you picked up this really heavy thing, you may want to say, well, it's okay to go at 1,000 meters per second, but take it easy getting up to speed and start slowing down sooner, right? Because when you got a big heavy load, you need if you're jerking around a lot, that puts a lot of extra stress on the joints of the robot. And so so you may want to say, well, I do want to go as fast, maybe as fast as I can, but I don't want to speed up too fast, because if I speed up at a easier rate, it'll be less wear and tear on the robot. All right, and also less chance that it might slip out of the gripper of the robot. Okay. And then we can do offsets. Okay, I was talking about the user frames and the tool frames before. Well, we can do an offset, which would be a user offset based off of the user frame. Or we could do another one. I don't know why I have offset here. The second one should be tool offset. So we can do a tool offset, which is an offset based on our user tool. Okay. So those are just a few of the options. And again, more options would be available if you added extra software also. But this is even just from the default software. It's just a few choices there. All right, so let's go ahead and flip over to the program now. So here's the Roboguide software, and I have this. Let me clean it up here for a minute. I have this brown box fixture here. I talked a little bit about adding the fixtures there last week. So I've got this fixture, and here is this brown box. Okay, and so I've created several different programs in here, and so I'm going to start with the default program called Shapes. Okay, now this program right here uses the joint, right? You see here is my joint type of motion, and so but it's doing a fine termination. All right, so it's going to go to point 1 to point 2, and these points are showing up over here. I don't know how well you can see that. So like, this is point 3. So the points are the corner of the box. So what this is going to do is it's going to go to each corner of the box and stop, and then move to the next point. So it's not going to stay at each corner, but it's actually going to stop. So if I run this through here, you'll see this move. Got to enable your teach pendant to run it in teach mode. All right, so you'll see it. You know, this thing's moving so fast. Let me slow it down a little bit. But you see it here as it moves. Okay. And you see that it's not moving in a straight line. You can really see that on these long things. It looks almost like from point 4 down here to point 5, it looks maybe like it was a straight line. But if we look at it from the top, all right, you can see that there is some curve in there. So it's not perfectly straight, all right? So some of it's just the angle. But you can definitely tell from going from point 3 to point 4, okay, this blue line is showing you how it moved, right? Let me slow it down even more here. So just run it through here again. So you can watch this. Okay, and right there, notice that I told it, I'm telling it to start at point 4, which is down here. All right, but now, right now, it's up here. The robot is up here at point 1. Okay, so up here is point 1, but I'm going to tell the robot to start at point 4. So when I do this, notice it skipped point 2 and point 3. It went immediately to point 4 because that's where I started it in the program. All right. And so again, if there was something in the way, it would have crashed right into that object in the way. All right. So, but anyhow, the big thing here I wanted to point out is this joint sort of motion. So you see that blue line there is curved. That's a joint motion. Notice it is actually getting to point 4 and it's stopping at point 4, just not for very long. Okay. Or I don't know why I keep starting at point 4. Let me run it through the whole program here. All right, so we'll start at line 1 this time. So we come down to point 2, we're going to point 3, point 4. So you can see we're actually going to point 4, and maybe you can see just a tiny bit of hesitation there because it's it was physically stopping at each one of those points because I'm doing a fine termination. All right, so now I've got another version of the program. What I did was I just copied this program and I renamed it L, shape L, and that's because these are linear. Okay, so now these are all linear instructions here. So when I run this one, what you're going to see is it's going to move in a perfectly straight line right along the edge. Okay, so you see that it's moving right along the edge of this fixture. I'm running it one more time here. So it comes down, it's not following the blue line. The blue lines are what the joint motions were doing, right? But this is doing linear movements, so it's moving right along the edges of the box. Okay, so that's a linear movement. We know that we're going in a perfectly straight line. And we're stopping at each point. I'll run it one more time here. So we're going to stop at each point and then move along. Okay. All right, so along with that, I also have some choices here which are linear motions. So notice here, linear, 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 linear. These are all linear motions, but they have a continuous option on them, or termination. So remember, this is the fourth one is the termination. Not, I said option, I meant termination there. And so so I'm going to run this one. Now this is a continuous 0. So you might, you're going to notice this really looks very, very similar to the fine. Okay, it looks like it really touched each point. Maybe it kind of rounded that off a little bit, maybe not, but for the most part, it was almost identical. Okay, but it just didn't spend quite as much time at point 4 because or point 3 or whatever, because it didn't actually stop at those points. All right, so then let's go ahead and move to this one. I did a 33, and I'm going to run these all together in a minute, but I'll do one at a time. So this one is doing a continuous 33. Okay, so what that means is we're going to slow down quite a bit, but we're going to kind of knock off the corners. We're not going to quite get to the corners. Okay, and so as you can see here, it looks like it actually is still touching those corners right now, but I'm running at a slow speed. The other thing about this is as you speed it up, it doesn't get as close. All right, and so yeah, see, I run it at 100%. It just moves way too fast. But I'm going to run it in auto mode here, and it'll show us the traces, and we'll be able to see it. All right, so let's yeah. So let me just I'm going to come over here. I'm going to hit this, which I talked about last week, as a cycle start, so it runs in auto mode. So I'm running this in auto mode now, and this is the 33 choice. And notice what happens here is when I ran this, it never even got close to the corner. Okay, you see how it rounded that corner off. Okay, so that was the 33. Let's go back and run the 0 that way. Okay. All right, and so when I ran the 0 here, that trace is kind of hard to see, the color that it chooses. I don't know, it just randomly chooses a different color every time it runs it. And it just with the 0, it looks like it's pretty much right on that corner. Okay. And so I'm just going to come over here. If I come to this one called all down here, number 12, this here is calling all of those. So what it's going to do is it's going to call the shapes program, which was joint motions, and then it's going to call the linear one, but with fine termination, and then it's going to do the continuous 0, continuous 33, and continuous 100. And I just threw a weight in between all of them except for the line 1 and 2 here. So let me just, I'm going to add a weight right in there also. I got to turn my teach pendant on. I always forget that. This software, every time you hit the play button, it automatically turns off your teach pendant. And I always forget to turn it back on when I try to edit. All right, so I'm going to just throw in a wait instruction here and just have it wait for a few seconds. Okay. And wait at the end really is doing nothing. All right, so it's going to run through here. It's going to run the shapes. Now, when it does this, what I'm doing is I'm calling each one of those programs I've already showed you. Okay, I haven't shown you the 100 one yet, though. But you'll see it here when it runs. But the when it calls program 1, you're going to actually see the teach pendant here displaying those lines as it moves through them. Okay, and then it's going to call wait 5 seconds, and it'll call the next one, and so on as it goes through there. All right, but it's going to show the traces over here as we see it move. Okay. So let me just run this then. Okay, and so I'm just going to go run this in auto. But I'm going to slow it down a little bit. Okay, so you notice the joint movement, there's the linear movement. Okay, this is the linear with continuous 0. This is continuous 33. And that one there was continuous 100. All right, so let me, I'm going to, I guess I'll delete these. Let me delete these lines here for the first 2. Turn my teach pendant on. Okay. All right, so I'm going to start it at continuous 033. So I'm just going to do those 3 so we can see what those are doing here in a little more detail. Okay. All right, and I'm going to kind of change my angle here a little bit. And okay, so I'm going to slow down here a little bit, but we can see there. Okay. For one thing, okay, so you see this here, I slowed it down to 45%. And so what you notice here is you see how close even the 100% got down here near this corner. Okay, narrow corners at the bottom there, you can see I got pretty close. All right, but if I run this again and let it go up to full speed, okay, it always defaults to full speed. Watch what happens. Okay, now it's exact same code, but watch this 100%. You see what a huge look at that. I mean, it looked almost like a big circle over there. It really just kind of wrapped around there. So when I ran those at different speeds, my time here 51. Okay, so that was this one. Okay, this is the one here that I ran before that. Okay, it was the exact same program. This one was the exact same program, but you notice how right along the edges, especially these long edges, it's touching those edges. Okay, even in the 100. But when I sped it up to 100%, it ran at a completely different speed, and it just barely touched this edge over here. Okay. So when you change the speed of the robot, the path may change. Now, if you're doing linear with fine termination, it's not going to change. But if you're doing joint motions, or you're doing linear motions, but with continuous terminations, these paths are going to change. See, look how, you know, here along this bottom edge here, okay, right along this bottom edge, it never even touched, when it was in the 100th, it never even touched this bottom edge. But if we go back to the one I ran previous to that, it was running along the edge near the center of it. Okay, so it's very important to understand with these motion instructions is that you may not understand exactly where the robot's going to be traveling. All right, so you know, with this 100th, okay, let's go look at the program. I don't know if I showed it to you before. All right, this 100 program, it's a linear motion, so it's supposed to be moving in a straight line, right? This is supposed to be moving in a straight line, but because I used a continuous, it gave me this line here when I did continuous 33, and if I click on this one, this is what the path that it took when I did continuous 100 at full speed. So I'm sorry, I said that wrong. This is continuous. These are the same. This is 133 and 0. So they're all the same continuous, but this colored one here, this kind of magenta sort of color, was at 45% speed. But this one here was at 100% speed. All right, so simply by speeding up or slowing down the robot, the path that it may make is different. Okay. So you have to be just, you know, very careful when you're working with these motions, that you understand how that arm is going to move, because if you don't, you know, you may accidentally run into something. All right, so but that's pretty much it for the motion instructions. Okay, there's this week, normally, you know, this week we would have a quiz and a assignment, but I only have a quiz out there this week, so there's no assignment to look for. There's just a quiz. It should be open now. Should be available, but don't be looking for an assignment. There's just the quiz piece.